All right, so this should be the last lecture of the semester. I'm going to talk a little bit about cohomology. I think I'll go ahead and skip most of the proofs and the constructions and focus on the properties and sort of what can you do with cohomology and what's it good for, and how do the basic computations look. All right, so let's go ahead and do that. Okay, first of all, what sort of objects are we studying here? So if we have F, coherent sheaf, or I guess we're doing quasi-coherent here. On let's say on a variety. Over a field K, then we'll have H, P, X, F. This is a P here. This will be a vector space over K. All right, and what are these vector spaces? What are they good for? Okay, so let me tell you a few important properties. So H0 of XF will just be the vector space of global sections. All right, so this is sections of F. Okay, and then what do the higher ones do where P is bigger than 0? So what they'll do in that case is they'll sort of measure the failure of surjectivity. So given an exact sequence, of sheaves F1, F2, F3 to 0, then we've seen that this here is exact. So let me write that like this. Okay, okay, but the point here is it's not exact on the right. It's over here. This map may not be surjective. Okay, and the cohomology is going to help us fix that. So if we continue on, we can put right here H1 of X, F1, H2 of X, F2. Oh, sorry, that's wrong. These are all H1s. H1 of F3. And then continue on to the next row, H2. And continue on. And that will give you an infinitely long exact sequence. Okay, well, it's usually not infinite. Eventually, these will all become 0. We'll talk about when you can know when that happens. But you get a short exact sequence turns into a long exact sequence of sections. And you can think about that as sort of measuring the failure of surjectivity of this map here. So just example that you should keep in mind that we've seen before is we had this map here. So O minus 2 on P1 mapping into O P1 mapping into, let's say, OP direct sum OQ to 0. Okay, so what are these here? This is these are skyscraper sheaves. At points P and Q, which are points of P1. This is the structure sheaf. What's this map here? This map would just basically be evaluation at the points, right? Okay, and this here you can think of as the ideal sheaf. Of P union Q. You could think of this map as being something like phi, like a function of degree minus 2 maps to phi times f, where the vanishing set of f is equal to the set. Maybe I'd rather write the set P, Q. So you can pick a degree 2 polynomial that vanishes at 2 points on P1, the P and Q, and that will define for you this map here. Okay, and why am I showing you this this sequence? Well, this is an example of a sequence where the corresponding sequence of global sections is not exact. So here we'll have the sequence of the global sections will be 0. What are the global sections of O minus 2? Well, remember, that's just 0 because the minus 2 is negative. The global sections of the structure sheaf of a projective variety is always one-dimensional, so this will just be the vector space K. Okay, but the global sections of a skyscraper sheaf is once again just K. So it'll just be K, well, 2 copies of K here. And okay, so this is what we have here. This is exact so far, but it is easy to see this map can't be surjective. All right, so but what we will see is that there is a cohomology group here, H1, P1 for O minus 2. And this is the thing that will make it so that we have exactness here. And of course, then it continues on to H1 of the structure sheaf, which we'll also talk about that. Okay, so that's an example, maybe the easiest example to keep in mind of the failure of surjectivity of global sections. All right, let's talk about some other first properties. So maybe the most, we already hit the 2 important properties, that we have the existence of this long exact sequence, and we have the identification of H0, the global sections. I mean, so really, I mean, we can write this term here, F1 of X is just H0 X F1, and similarly for these ones. Okay, okay, but let's do a few more properties. So if X is affine, then HP of X F equals 0 for all P greater than 0. All right, the idea behind this is, remember, if X is affine, then quasi-coherent sheaves correspond to modules, right? And then the global sections correspond are just the same modules. So an exact sequence of sheaves is an exact sequence of modules, and that same exact sequence is the sequence of the global sections. Does that make sense? So maybe I should try and say that. So 0, F1, F2, F3, these are quasi-coherent on an affine scheme, and this just corresponds to M1 tilde, M2 tilde, M3 tilde, and then the global sections is just, are just the modules themselves. And I believe we had a lemma back a while ago that said that, this is exact if and only if this is exact, if and only if this is exact. So there's no problem here with the surjectivity of this last map. It's sort of automatic. So in that case, the cohomology groups just equal 0, and then the long exact sequence of cohomology just becomes the short exact sequence of global sections. Okay, so cohomology really is interesting. When we're dealing with the gluing and stuff. It is not so useful for studying affine varieties. All right. Now you might be interested to know how long that sequence goes on. If it goes on forever, then you might have a hard time doing something with it. But in fact, it's usually finite. So if X is projective of dimension n, then HP XF equals 0 for all P greater than n. All right, so the cohomology groups are bounded by the dimension of your variety, of a projective variety. All right, then part C, if we have inclusion from Y to X, so this is of a closed subvariety. Um, then we'll have an isomorphism. If you have a sheaf on Y and you push it forward, so let's write it like this: HPX, the push forward of F, that will be the same as just taking the cohomology of the sheaf on Y. Okay, so this kind of shows that the cohomology is sort of not sensitive to any extra things that are happening away from the support of the sheaf, right? So if the sheaf is really a sheaf on Y, it doesn't matter if you put Y into a bigger space, then you still have the same cohomology. All right, so we'll see that using these long exact sequences, we can often compute the cohomology of sheaves if we know how to construct the sheaf out of other sheaves. But we got to have somewhere to start. So what are we going to start from? The sort of basic building blocks are going to be the Serre twisting sheaves that we've talked about a few times. So for example, we've seen using the Euler sequence how you can get the cotangent bundle from Serre twisting sheaves. So let's try and, or not try and, but over there, I'm going to give you the cohomology the Serre twisting sheaves. All right, so here's part A. The global sections on Pn of OD you can identify with just polynomials, homogeneous polynomials of degree D. Okay, I think we've basically already seen this, right? This follows from the definition, I think, pretty easily. I think we already mentioned that. Because remember, this is the same thing. It's just the global sections of OD. All right, now let's look at Hn of Pn OD, where we're looking at the nth cohomology group where the n matches the dimension of the Pn. All right, this is going to be isomorphic to 1 over x1, x0, x1 through xn times the polynomial ring, or the Laurent polynomials. And then take the degree D here. All right, so in other words, you have to have the D be negative, so it equals 0, unless D has to be actually less than minus n, right? Okay, or less than or equal to minus n minus 1, right? Because this piece here already, this thing here already has a degree negative n minus 1, and yeah, so to have any hope of sections, you need to have the right negative. All right, and then part C of this lemma is that those are the only cohomology groups. So this is going to be automatically 0 if P is not equal to 0 or n. Okay. Now, this expression is sometimes useful, but a lot of times all you're interested in is the dimensions. So let's write those down here. There's a common notation that if you write a lowercase h, so lowercase h0 of Pn OD, this just by definition is the dimension of the vector space. Here, okay, and well, we can compute that here. It's just n plus d. Choose D. This is the number of degree D homogeneous polynomials in m plus 1 variables. So you can think about why that's the right formula for that. And then let's write down the formula for Hn. All right, it'll be a minus d minus 1, choose n. Okay, and once again, I'll let you do the combinatorics on that. And this is also maybe we should know that you can write this as n plus d, choose n, that's the same thing. Also, let me remark that if d is negative, then the h0 is equal to 0. That follows from this formula, or from this expression, or from our previous computation. So we're okay with that already. All right, so this is an important thing to remember. So the cohomology groups of a Serre twisting sheaf, there's only the 0th or the nth. And in fact, only one of them will be non-zero at a time, right? If the d is positive, then it will have some h0. If the d is very negative, then it will have some hn. If it's in between, then it won't have any cohomology at all. Or in other words, it will all be 0. And okay, so that's the cohomology of Serre twisting sheaf. All right, with this in our hands, let's scroll back up to our example here of the double skyscraper sheaf sequence, and we're looking here at this group H1 of P of the Serre twisting sheaf by minus 2. So according to according to the thing we just computed, this should be isomorphic to 1 over x0, x1 times the polynomials with negative coefficients, and we're taking the degree minus 2 piece. Okay, and of course, or using the formula, this is just one dimensional. It's just our vector space k times x0, x1. All right, so this is isomorphic to k, which is kind of what we expected. What's the next group in the sequence? So let's go down to the next line. The next group would be, so we did h1 of this thing here. So next thing is h1 of the middle term. So I'll have h1 on p1 of OP1. Now the calculation of the structure sheaf, cohomology of structure sheaf, that's included in the calculation of the Serre twisting sheaves, right? Because that's just the twist by 0. And okay, and this is going to be equal to 0, right? So I'm going to write that right here. Okay, well, why is it equal to 0? Well, it's the degree 0 part of this thing, but there's no degree 0 part. Everything has a negative degree, strictly negative degree, or you can just use the formula too. Okay, so that's 0. So our sequence terminates right here. I mean, it's possible that you get a 0 and then you have more groups later, but if you're sort of interested in what's happened with the global sections, then once you get to a 0, you can kind of stop there and you just have an exact sequence right here. So it's k mapping to k plus k mapping to k, and that mostly makes sense, or that makes sense. That's an exact sequence. In fact, we can kind of describe these maps pretty explicitly. So this k just corresponds to constant functions on P1. And then this map, remember, corresponds to evaluation of those functions. So this will just map to a comma a, all right? And then this map is sort of what's called the connecting homomorphism in the long exact sequence. So it's just sometimes a little more tricky to describe, but we can mostly deduce what's going on here because we know exactly what its kernel is. Its kernel is A, so this must be something like A B maps to A minus B, and then the kernel is exactly this here. Okay, so hopefully that makes sense. Okay, so now we've talked a little bit about how cohomology helps us compute global sections and see how they behave and measure this failure of surjectivity. Another very important use for cohomology is when we're dealing with the classification of varieties. These can give us some variance, some numbers that we can compare to see whether two varieties are isomorphic or not. All right, so let's see what we can do with that. The first thing we're going to do is define a certain combination of the dimensions of the cohomology groups that is more this better behaved, more useful often. So this is called the Euler characteristic, and it's usually denoted by the Greek letter chi. So if I write chi of x f, this is defined to be the alternating sum minus 1 to the p of the dimension of the pth cohomology groups. All right, I'm going to write p equals 0 to infinity, but for example, if x is a projective variety, in fact, this will be a finite sum, right? Okay, and also if f is a coherent sheaf, then it turns out all these dimensions will be finite numbers too. So this will be well defined. Okay, now the point is that so here's the good property. If we have an exact sequence of sheaves, then the Euler characteristic is additive. So the Euler characteristic of the middle thing is the same as the Euler characteristics, or the sum of the Euler characteristics of the outer things. Okay, why does this work? So, so the thing we should recall is we have a long exact sequence of vector spaces like this, right? Let me not write x, I'll just write h0 of the f's, and then h1 of f. And then it continues on. Okay, so we have our long exact sequence. Let's write one more time. No, I'll put the dots. Okay, and the point is the alternating sum of the dimensions is equal to 0. All right. So what do I? So how does that work? So, I mean, if we take this one with the sign 1, this one with the sign -1, and this one with the sign 1, -1, 1, -1, 1. Okay, and then added up all those dimensions, then we get 0. So you can think about exactly why that is. That follows easily from the definition of an exact sequence and the way dimensions work in exact sequences. All right, so if we do that, okay, but then you can see how this breaks up, right? In this column here, this will just be the Euler characteristic of F1, and then this column here will be negative of the Euler characteristic of F2, and then this column here will be the Euler characteristic of F3. Okay, and so you recover this formula. Okay, so this is very nice if you have a sheaf that's constructed and it comes from an exact sequence, two things that you already know about, then you can deduce this Euler characteristic. Okay, and the Euler characteristic in this sense is better behaved than just taking the dimensions of the space of global sections, for example, or any individual cohomology group, because it has this nice additivity property. Okay, let's go ahead and start by computing the Euler characteristic of the only sheaf we really know as far as its cohomology. So the Euler characteristic on Pn of the Serre twisting sheaf will just be n plus d, choose n. All right, let's check if that follows from what we know about it. So if d is bigger than or equal to 0, then we already know that h0 of Pn O of d is n plus d, choose n, and we also know that all the other ones are 0. All p greater than 0. Okay, so we get exactly what we want. So now let's do the case if d is negative, but bigger than minus n. Then it follows from what we said that HP I think I'll see bigger than or equal to, I think is okay, right? Then this is equal to 0 for all p. So that means the Euler characteristic of OD would have to be 0. Does that make sense with this binomial coefficient? And the answer is yes. If you remember the definition of this binomial coefficient is you just take n plus d times n plus d minus 1 all the way dots down to you want to have n terms on top here, so you'll go all the way down to d, and then you have to divide by the n factorial, right? So I think that's the definition, and so you can think about it if d is between 0 and minus n, then at least 1 0 will show up in this numerator. So you'll get 0 here. Okay, now let's consider the case where d is less than or equal to minus n minus 1. Then HP of OD equals 0 for all p that are not equal to n. And then we have Hn of OD will be equal to, let's see, I believe it was minus d minus 1, choose n. So that tells you that the Euler characteristic of OD will have to be this minus 1 to the n times minus d minus 1, choose n. And you can think about that. That's actually the same as what the thing we want. All right, so I'll let you think about this binomial identity here. All right, let's look at this result one more time. The Euler characteristic, we get one nice answer that works for all d positive or negative or anything. So this is an example of how the Euler characteristic is a little bit better behaved than just taking the dimensions of cohomology groups. If you just take the dimension of the different cohomology groups, you need like 3 different formulas, depending on different cases. But if you just want the Euler characteristic, then you get one nice formula. So really, if you want to think about the cohomology of projective space, you just need to remember this one formula, and then remember that if d is positive, then you might have some h0. If d is negative, you might have some hn, and then the Euler characteristic is given by this, and that determines it, right? Okay. All right, let's do something a little bit more involved, not much. So let's let x be a degree d hypersurface in Pn, and let's try and compute the Euler characteristic of the twisting sheaf OX of V. So remember, OX of V by definition is just the pullback by the inclusion of OPN of V. Okay, now there is an exact sequence here for X. So the ideal sheaf of X is just O of minus D. All right, so this is sort of the standard exact sequence for x, and now what we're going to do is tensor it by d by e, and we'll get OPN of e minus d into OPN of e, and then here we'll have we'll get exactly OX of e. All right, so you can think about why tensor product sort of commutes with the restriction. So you can take OPN of e and then restrict it, or you can restrict the structure sheaf and then tensor by OPN of e, and you get the same thing. All right, so we have this exact sequence, and so now the thing that we want is appearing right here. Okay, and these two things we know because we already have that formula. So we have a Euler characteristic of OPN of E is equal to Euler characteristic of OPN E minus D plus Euler characteristic of OX of E. Okay, and I'm not writing the space here because the space is already in the subscript. So there you go. And so now we just plug into our formula, and we get a nice formula for this. It'll just be E plus N, choose E minus E minus D plus N, choose E minus D. Or actually, it's probably easier to write, and it's equal to the same thing if we write it like this. Okay, so there's a formula for a twisting sheaf on hypersurface. Let's go ahead and do an example here and apply this to a plane curve. So this is a curve in P2 that's defined by an equation of degree d. All right, and let's just apply it to the structure sheaf. So in that case, we'll have H0, the dimension of the space of global sections of the structure sheaf, minus the dimension of the first cohomology space. This is equal to the Euler characteristic of the structure sheaf, and we know what that is by the formula that we just wrote down up here. It's equal to n 2 choose 0 minus 2 minus d choose 2. Okay, and so that's 1 like this. Okay, the other thing we know is that remember the space of sections of the structure sheaf on a projective variety. This connected projective variety will just be a dimension 1. So this will be 1 here. So this is going to tell us that H1 of C OC is equal to 2 minus D choose 2, which you can write as D minus 1, D minus 2 divided by 2. Okay, this number here is called is often called the genus of the curve. All right, and this is an invariant of the curve, meaning that if you pick any curve, it has a structure sheaf, right? And you can take the first cohomology group of the structure sheaf, and it sort of doesn't matter how the curve was defined or where it came from. You can always take this number, and if the curves were isomorphic, you should get the same number no matter where the curve came from originally. So so this is an important number called the genus of the curve. It also has an important geometric interpretation. So if your field K is equal to the complex numbers and the curve is smooth, then this is also the topological genus. All right, so remember a curve over the complex numbers is actually kind of looks like a surface. So it's sort of the number of handles in the surface. So this would be a genus 2 curve. All right, so that's a slightly deeper fact, but a good one to know. All right, so here's one way you can use this for a basic result. So if you have two curves, C1 is degree D and C2 was, let's say, degree E, and then C1 is not isomorphic to C2 if D is bigger than E, and they're both bigger than let's see, I guess this would have to be bigger than 2, right? Because if you just look at this, formula for the genus here, if you put different numbers in here, you're never going to get the same number unless you pick a 1 and 2. So if D equals 1, E equals 2, so this is like a line in P2 and a conic in P2, then in fact that they are isomorphic. So in this case, the genus, or I guess the plural is genera. The genera match. And in fact, they are isomorphic. They're both isomorphic to P1. Okay, so let me just emphasize that just because the genus matches doesn't necessarily mean they have to be isomorphic. There are non-isomorphic curves with the same genus, but in this case, it turns out they are isomorphic. For P1, there's only one isomorphism class. Okay. All right. Good. Okay, let me make one more remark, just something to be a little bit careful of. So in the same situation, let's look at the Euler characteristic of OC1, where this is the twisting sheaf O1 restricted to the curve. If you plug that into our formula, you'll get, I'll just write it down quickly, you can check this. You get this, and this simplifies to d squared plus 5d over 2. And notice here that this is not an isomorphism invariant, because it right, if I plug in our case here, d equals 1 or d equals 2, you actually get different numbers. So what's the problem here? The problem is that this number here depends on embedding, right? So if you take the O1 sheaf and then restrict it down to the curve, it depends on how the curve was embedded. So even though in this case here the curves are isomorphic abstractly, that they're embedded sort of in different ways with different degrees. All right, so we have to be careful about that. The reason that this one here, this genus was an isomorphism invariant is because O1C, that's just the structure sheaf of the curve. That does not depend on the embedding at all. It's just the structure sheaf of the curve. Whereas this OC twisted by 1, that will depend on the embedding. All right, so we do need to be a little bit careful about that. Let's try and do a similar thing for hypersurfaces. In P3. All right, so once again, we can look at the Euler characteristic of the structure sheaf, and we'll get 1 minus 3 minus t, choose 3. Okay, now there's a few things that are different in this case. First of all, we can't identify this as the dimension of a cohomology group because this Euler characteristic here has 3 parts to it, right? There's the H0, there's negative H1, and there's also the H2. So of course this is still 1, but then these two things together will be equal to this. So you have to be you have to know a little bit more about what's going on to be able to identify which of these is contributing to that number. Okay, the other thing to notice is that if d equals 1, 2, or 3, then we have the Euler characteristic. Well, then this binomial coefficient here will be 0, and so the Euler characteristic will be 1. All right, so we have 3 different types of hypersurfaces, but it turns out these are not isomorphic, so are not isomorphic. So for d equals 1, you just have P2 included in P3, just sort of a hyperplane section. For number 2, an example of that would be a P1 cross P1 inside of P3 by the Segre embedding. So I think we already saw that's a hypersurface of degree 2. For degree 3, we haven't said too much about it, the cubic surface. We skipped this section on the cubic surface. It has 27 lines, so that's an interesting example. But of course, P2 has an infinite number of lines. So okay, yeah. Anyway, these turn out to not be isomorphic, but the Euler characteristic cannot help you tell them apart. Okay, if d is bigger than 3, then I believe the Euler characteristic will distinguish all the other ones. Okay, let's look now at something that will help us tell these apart. All right, so in general, let's look at X, a hypersurface in Pn of degree d, as we've been looking at, and let's try and now compute the Euler characteristic on X of the cotangent bundle. Okay, and this will give us a nice invariant, right? Because the cotangent bundle is defined for any subvariety or for any variety, so this doesn't depend on any embedding or anything. All right, so how can we compute this? Well, first let's look at the Euler sequence. So we have omega Pn mapping to O minus 1 to the n plus 1 mapping to O. Right, and this is a sequence on Pn, but we can go ahead and restrict it. It's a sequence of locally free sheaves, so we can restrict it to X. So let's, if I is the inclusion, we'll take I pull back here, and if I do the I pull back here, then that's just the same as changing the subscript from a Pn to an X. So let's just do that. All right, so that will give us the restriction. So from this, we in principle have enough information to compute the Euler characteristic of the restriction of the cotangent bundle here, because we already know formulas for these. Okay, okay, but that's not actually what we wanted, but it's close, or rather, I should say, it's closely related to what we want by the conormal sequence. So if you remember that, it looks like this: Ox minus t restriction of the cotangent bundle, and that will give you the cotangent bundle of X. All right, so see, we know this from this sequence here, and we already have a formula for this. All right, so maybe I won't write down the computations, but if you put it all together, you get the Euler characteristic of the cotangent bundle is just equal to this formula here. Okay, so that's just combining these exact sequences and using the additivity of the Euler characteristic. For our special case of P3, if you expand all those polynomials out, you'll get this degree 3 polynomial right here. And it's easy to see that for d bigger than 0, these are different numbers. All right. So that shows that the hypersurfaces of different degrees in P3 are always are not isomorphic. Okay, so this is sort of the power of these invariants. You can take sort of a geometric problem that seems kind of hard. Are these two things isomorphic? And then you sort of turn it into a mechanical problem of computing numbers and comparing them. Okay, good. Let's also apply this Euler characteristic of the cotangent bundle to our case of curves. So let's go back to a curve in P2. In this case, the Euler characteristic of the cotangent bundle. Well, remember the cotangent bundle is the same as the canonical bundle. So let's go ahead and write it like that. And that will be equal to d squared minus 3d over 2 if you just plug things into this formula up here. And this number might look familiar to you. This is just equal to minus 1 times the Euler characteristic of structure sheaf that we looked at earlier. Okay, so you might wonder if, so first thing to notice is that this doesn't give us a new invariant, right? If you were trying to hope that this would help you tell more things apart, this doesn't help. The other thing you might wonder is whether this is sort of a coincidence that this worked out this way. And it turns out there's a bigger thing that this is a consequence of that's quite important, so it's worth mentioning. It's called the Serre duality. All right, this works for any coherent sheaf on a smooth variety. In fact, you don't quite need smooth, but smooth is good enough. And it says that if you look at the p cohomology group on X of any coherent sheaf X, and let's take the dual of that. This is a vector space, so we can just take the vector space dual. This will be isomorphic to H n minus P, where n is the dimension of X. And then here you have to take the canonical bundle and tensor with the dual of F. So this is now the dual of the coherent sheaf F inside of the parentheses. All right, so this is Serre duality, a very important and much used tool when you're dealing with sheaf cohomology. Okay, so how does that affect, or how is this relationship here a consequence of Serre duality? Well, so now let's let X be our curve, and let's let F just be the structure sheaf. All right, so we can notice that the dual of a vector space has the same dimension. So this in particular would give us that let's say H0 of X OX would have the same dimension as this group. So notice the dual of the structure sheaf is just the structure sheaf again, and if you tensor by the structure sheaf, then you don't change anything, so we just get omega X here. Okay, and then we can do the same thing when P equals 1. Then you'll have that this is equal to this dimension. Okay, and then let's just should we put minus signs on these ones and then add them up, and then this side will just be the Euler characteristic of OX, and this side here will be the negative of the Euler characteristic of X, omega X. Okay, and that's exactly what we observed up here, that the Euler characteristic of the canonical bundle was the negative of the Euler characteristic of the structure sheaf. All right, so there we go. So Serre duality is a very important tool in algebraic geometry. So let's color that yellow. All right, so I hope this lecture gave you a little taste of cohomology and some ideas of what it can do and what the sort of computations look like. If you combine these tools, the long exact sequence, the Euler sequence, the conormal sequence, the twisting sheaves, the computation of cohomology of the twisting sheaves, and then serduality. By the time you combine all those tools together, you can really compute the cohomology of lots of things and get some good information about how many sections something has, a sheaf has, or something like that. All right, so I think that's all for the semester. So thank you everyone for participating in the class, and I know it's been a little bit different with the virus situation, but I've enjoyed teaching, and I hope you've learned something.